Hi, welcome back to Enzyme Kinetics in Biochemistry and Physical Chemistry. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. Alright, so in this video we're going to discuss the generation of a Lineweaver-Burke plot. And we're going to go over basically how you do this, okay? And all of it that we're going to be doing is based on what we talked about in the last video, this hyperbolic graph of the Michaelis-Menten plot. Okay, of rate versus the substrate concentration. Okay, so one of the important things is that if you look at where the Vmax is and you understand what this curve is doing, the curve is increasing, okay, but it's essentially approaching this horizontal line, which is representative of the Vmax. Okay, in fact, it never actually hits that line because this line for the Vmax, whatever rate this is an asymptote. It's a horizontal asymptote, and this curve is going to get closer and closer and closer to the curve as the substrate concentration increases, but it'll never hit the curve, but it will approach it. So the question is, if you want to find out what the Vmax is from this plot, can you? And the answer is no. You can't figure out what substrate concentration yields the Vmax. Because if you were just doing it according to this plot, what would you have? Well, when do you get closest to this Vmax horizontal asymptote? Well, it's technically when the substrate concentration is infinity, right? So if you're doing the limit as the substrate concentration goes to infinity of the rate, then that's the Vmax. But as we'll talk about in the next video also, what's the problem with this? How can you have a substrate concentration of infinity? Number one, you can't have infinity molecules in a cell or in the lab for that matter. That's impossible. If you tried to concentrate an infinite number of molecules to get an infinite concentration, that's impossible. There's limits to solubility. So this obviously is not true. It's not possible. Graphically, it appears this way, but it's not true. It turns out that what we're going to find is the actual Vmax occurs when the enzyme is saturated with substrate, which is certainly a finite number of substrates, but it has nothing to do with the substrate concentration going to infinity. So how can we actually figure out a number in terms of what substrate concentration produces the maximum rate? Because that's what we're going to find, is the actual rate of the enzyme is largely dependent on how much substrate there is. If you have too little substrate, then you're not going to see a fast rate of the enzyme. However, if you saturate the enzyme with substrate, you're going to see the maximum rate. How do we find that? Well, what we're going to do is we're going to derive an equation, a very simple equation, called the Lineweaver-Burke equation. And from it, we're going to generate a Lineweaver-Burke plot. All right. So what we're going to do is we're going to start with the Michaelis-Menten equation that we talked about in the last video. That is, the rate of the enzyme is equal to the Vmax times the substrate concentration divided by the sum of Km plus substrate concentration. The first thing I'm going to do is I'm going to take both sides of this equation and take the reciprocal of them. Okay? So when I do take the reciprocal of V, that's 1 over V. Then when I take the reciprocal of this fraction, it's just that the denominator goes up to the numerator, Km plus the substrate concentration. And then the numerator goes to the denominator, Vmax times concentration of S. Okay? Now notice I have a sum in the numerator now and just some one term ultimately in the denominator. So what I can do is when I have 1 over V, I can set that equal to now just Km divided by Vmax times S, and then plus substrate concentration divided by Vmax plus S. The beauty in this actually is that, notice, in this term over here, substrate concentration cancels, and so in this term you're left with basically 1 over the Vmax. And then in this term it's going to be Km divided by Vmax divided by substrate concentration. Now, if you go back to this original graph, this hyperbolic curve we had, you think about what is actually the independent variable. Well, the independent variable is actually substrate concentration. That's actually the variable we're concerned with, and then the rate is the dependent variable. So my question to you is Km a variable? And the actual answer is no. Km is a constant, and it turns out that also Vmax, these are constants. They're constants for a given enzyme, so at a certain condition. okay, like temperature or pH. So we're assuming temperature and pH are constant, so Km and Vmax are constants, all right? So now I have a substrate concentration, which technically is a variable, so that means 1 over substrate concentration is also a variable. So what I'm going to do is, for this term, I'm going to take the Km and Vmax and pull them out as one fraction, and then I'm going to have 1 over substrate concentration multiplied by it. So ultimately, the equation I get is 1 over the rate is equal to Km divided by Vmax times 1 over the substrate concentration plus 1 over the Vmax. Now, here's the important thing. This now is in the form of y equals mx plus b. There's an old saying in physical chemistry and some other areas too that pchem, or physical chemistry, is the pathetic attempt to force everything into a straight line. Now if you just took this equation, the original Michaelis-Menten equation, that's obviously not a straight line, it's a hyperbolic curve, all right? So you can't really do much in the way of that, but if you force this into a straight line, it becomes exceptionally easier to calculate the Vmax and Km values, okay? So here's what we're going to do. We're going to say that 1 over V is y, okay, in the y equals mx plus b equation, all right? And you can actually do that. You can have a fraction of a function equal to the dependent variable. You can do that. Now because Km is a constant and Vmax is a constant, their quotient has to be a constant. And in a straight line, right, the slope is a constant. It's just some number m. So Km over Vmax corresponds to m, the slope of the line. And just like you can have y as 1 over v, you can have x as 1 over substrate concentration. So this 1 over substrate concentration I'm going to say is our x. And then Vmax is a constant, so 1 over Vmax is also a constant, and that's going to be our b, our y-intercept. Okay? So ultimately what we're going to do, and we'll actually look at real data in another video, but for now, we're just going to look at the general form of a Lineweaver-Burke plot. Okay? So unlike a lot of other plots that you see in chemistry and physics, for this one, yes, you do have to use this quadrant over here, but you're actually going to have to go into the negative side a little bit also. And what you would find is, generally the way this type of plot works is what you're given is you're given a substrate concentration and you're given a rate that goes with it, right? So this is the first substrate concentration, this is the first observed rate. Then what they do is they change the substrate concentration 2, and that changes the rate, V2. Okay? Then they change the substrate concentration again, and that corresponds to another rate. And then they keep changing the substrate concentration, and you get a new rate each time, right? So you have one substrate concentration, one rate, and they're basically points on a graph. But here's the problem. Our y-axis is 1 over the rate, and our substrate concentration is 1 over, or our x-axis is 1 over substrate concentration. So technically what you have to do if you're given these values to generate a Lineweaver-Burke plot, you literally for every single one of these that you give, and you could have many of these, you actually have to take the reciprocal of all of these. So if you have 30 points, you have to take basically 30 or 60 reciprocals if you're looking at both of them. So if you have a substrate concentration, take its reciprocal because the x-axis is 1 over s. If you have a rate, take 1 over the rate because the y-axis is 1 over the rate. And then once you get these points, so if I have a 1 over substrate, oops, let me do it like this. So 1 over v, comma, 1 over substrate concentration, then you just plot that point. And perhaps you get a series of points like this. Okay? And then what you would do, and we'll do this in another video more experimentally, you go into a program like Excel or on a Mac, it's Numbers, and you plot a linear regression line, okay? And what that's going to do is give you a line like this, and you can actually set it to where the line will actually go through the y-axis and actually hit the negative x-axis over here like this. Sometimes when they do this, you'll only see this part in the first quadrant right here. You can actually set it to where it'll go into the negative x part right here, and it'll hit the negative x-axis, and this is actually the x-intercept right here. Okay, so this is your Lineweaver-Burke plot. Now, how do you actually go about calculating the Vmax or the Km value? Well, it's actually really not that hard. Say, look at this point right here, the y-intercept. You remember the y-intercept b is just 1 over Vmax, right? So, what's the y-intercept? Well, the y-intercept is just a number. And suppose the y-intercept, I don't know, I'm just making up a number. Let's say the y-intercept was 5. So the y-intercept was 5. How would you calculate the v-max? Well, if the y-intercept is 5, that's also 1 over the v-max. So if you want to find the v-max, you just basically take the reciprocal of all this. Take the reciprocal of 1 over v-max, that's the v-max. Take the reciprocal of 5, right? So 1 over 5, or that's 0.2. And of course, I'm not including units, but hopefully that gives you the idea. Whatever the y-intercept is, that y value, you just take the reciprocal of it, and that's your v-max with whatever units you were using. Okay? That's actually the easier part. A slightly more difficult part is actually calculating the km. And this is why you actually have to set your Excel file to extrapolate down to the x-intercept, which is actually always going to be on the negative x-axis. Okay? So it turns out this dark blue point is actually equal to negative 1 over the km. Okay? That's what this is equal to. So let's suppose for this value, this negative 1 over km, I don't know, let's say this was equal to negative 7, I don't know, something like that, just making up numbers at this point. Well, how would you figure out what this is? Well, number 1, multiply by negative 1, right, on both sides. That cancels the minus sign, right? So that's probably the first step you want to do. Cancel the negative, right? So now what I have is I have 1 over km is equal to 7. So now I just do the same thing from before. I actually just take the reciprocal, and I get that the km value is equal to 1 over 7. I think that's approximately 0.143. Okay, and that's how you would figure out the km. So the thing about a Lineweaver-Burke plot is generally what you have to do if you don't have, well, in any case, you really should go ahead and just use Excel and figure out a linear regression line, and then it becomes a lot easier to extrapolate these things. But if you're actually just doing this graphically from data without a computer, you can generate a line, figure out where it hits the x-axis. It's going to be on the negative side. Take the reciprocal and the negative of that value, and that's the km value, and then look at the y-intercept. Take the reciprocal of that, and that's the v-max. Okay? So that was the derivation of the Lineweaver-Burke plot. And then these are sort of the critical values on the Lineweaver-Burke plot. Okay, 1 over v-max is the y-intercept. The x-intercept is negative 1 over km. Okay? Now remember, there's a very important thing you have to remember when you're plotting data for a Lineweaver-Burke plot. The y-axis is 1 over v, and the x-axis is 1 over s. So you're probably going to be given s and v. You have to remember to take the reciprocals of those. So 1 over s1, 1 over v1, 1 over s2, 1 over v2, and so on and so forth. Those are the values that you actually plot. Because generally what you're doing is you're plotting the y value, which is 1 over v, and the x value, which is 1 over x, or 1 over s, excuse me. You just plot the x value, plot the y value, and you get a series of points like this. And the thing about the Lineweaver-Burke plot, because the derivation forces it into a y equals mx plus b form, the line should theoretically be pretty straight. Okay, if you do this with Excel, you can have it generate a linear regression line, and then you do those calculations we showed at the end to calculate km and the vmax. Okay, so hopefully this helped you understand the theory behind the Lineweaver-Burke equation and plot. In the next video, we're actually going to use an Excel program and some hypothetical data, and we're actually going to get a Lineweaver-Burke plot. Okay, and then we're going to figure out what the Vmax is using Excel, and we're going to figure out what the Km is also. All right, so hopefully this video helped give you an intuition of the Lineweaver-Burke plot and equation. My name is Kevin Tokoph. Make sure to like the video, subscribe to the channel for future videos and notifications. Thank you very much. Join us next time.